Okay, so let's talk about some general lessons learned, some conclusions we can draw from things that we saw. So, given what you all saw in the presentations, what are some conclusions you draw, both keeping in mind your own experiences and then seeing what other people had to say? General thoughts? Yeah, Mitchell.
Can you draw your letters in a similar
So, I don't know why I'm green, but here we are. Okay. Yeah, Dan.
A little more specifically on that, similar size and similar location is very important.
Size and location matter. Good. Other thoughts? Yeah, Silas.
variation in style? For all
Okay. Variation in style means more hidden nodes. Good. Yeah, David. I'm sorry?
Overall training size is extremely important.
Okay. And so specifically for your training, whoop, that is not a word. Train. Okay, let's try that again. I'm going to keep it green, of course. Training size should be large. Bigger is better when it comes to the number of training samples. Yeah, that's definitely true. All right, other observations. Yeah, Jake. Oops. Yeah. Double letters. It's important. Yeah, definitely. Yeah, Dan.
One thing I don't know exactly how this fits in there, but I was a little confused.
Yeah.
I can see how having more iterations might not gain you anything, but it seemed like in some of the results, more iterations actually lost you something, and I would consider that surprising.
Right.
It's going to converge.
Sometimes you can have too many iterations. And so this often leads to approaches where instead of having a preset number of iterations, you can say, have it test itself after each training iteration. And once you get to a certain threshold of accuracy, it just doesn't seem to be getting better at that point, you could stop. So that's something that people sometimes do in an automated way, as opposed to just having a fixed number of iterations. Yes?
I don't know, I still feel like we don't have any sense of where to go with iteration size hidden nodes for the learning rate. Like, I was blind the whole time.
Yeah, so this is a very much an opaque algorithm. Okay, and so this is something that one inevitably struggles with in dealing with the multi-layer perceptron. What it's even doing tends to be mysterious, and consequently, there isn't very good theory for it. Like, there isn't really a good generalized body of knowledge saying, with this kind of data, you should do that kind of thing. What tends to happen is that certain people will often just get a lot of practice with multi-layer perceptrons on some various data sets and start developing an intuition about how to parameterize it for a given data set in a way that is not readily transformable into rules, rules of thumb to follow. I mean, we've talked about a few things, like the fact that if you've got too many hidden nodes, it's going to overtrain. And certainly more data is better. And something that Eric pointed out that's just hugely important in practice is the pre-processing actually matters enormously. So fairly typical pre-processing for a task like this involves you can scale the sizes and then move to the centroid. So in other words, for a given letter, you can work out what's its center of mass, so to speak, thinking in calculus terms, right? So basically, I mean, these are just pixels, and so you don't really have to use calculus to determine it. You can just add up all the XY coordinates and find and divide by the total number of pixels, and that gives you a centroid. So you can translate each letter to a centroid and then scale it to fit a particular size, and only then even begin using the neural network. So doing that has a number of advantages as well as some disadvantages. The biggest advantage of that kind of a scheme is thinking about, in terms of engineering a system, where do we really know what we need, and where does a machine learning algorithm help us not have to get bogged down in details, right? So there's a sense in which we know if we're trying to classify letters, they really ought to be the same size. If we're comparing things to random bits of white space, that's not really going to get us anywhere. And so that kind of pre-processing can be well motivated there to then say, okay, so having figured out that we need to do X, we'll do X first, and then we'll throw the rest into this black box machine learning algorithm. The disadvantage of this, of course, is having to work out what kind of pre-processing do you actually need and what's useful, and at what point might you pre-process so much that you eliminate the need for a learning algorithm. I mean, that hasn't really happened so much with handwriting. Things like multi-layer perceptrons are really appealing for handwriting simply because trying to work out some algorithm to say, well, for a letter R, you kind of want a stroke going this way, and you kind of need a thingy up here, and so forth. It turns out to be less labor intensive to just annotate a whole bunch of samples and say, algorithm, go to town. But this idea of, scaling and stretching and centering and so forth, that's totally heavily used in practice. And they'll even do other things on top of that. They might recognize certain letters as special cases and have kind of their own separate classifiers for those. Like you can do multiple levels of classifier. For instance, you can imagine putting together a classifier that can say, well, it's got to be an O or a Q, but I'm not going to tell you which one. And then you might have some supplementary classifier that actually classifies them, and maybe, for an uppercase letter only looks at the bottom quarter of the image, or something along those lines. So when you're talking commercial grade handwriting recognition, lots and lots of hand engineered steps like that are extremely common and actually fairly important. Once you're getting to a point of being able to say, whether a letter reaches its destination depends on this, and that kind of a thing. But huge amounts of data are also very important. So one of the baseline training sets that are used for comparing lots of different machine learning algorithms is referred to as the MNIST set. And this is 60,000 samples of digits from 0 to 9. So typically you can take a fairly vanilla multi-layer perceptron. And the thing about the MNIST is they've done all of that stuff for you. So they've stretched them, they've centered them. These are super cleaned up images. So you can take a fairly vanilla multi-layer perceptron and be exceeding 90% very easily. But a lot of what makes that possible, of course, is the fact that you've got a lot of data samples. And they've been pre-processed. Furthermore, when we think about digits, 0 through 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, each digit really has some identifying characteristics that are going to help the algorithm to differentiate it. They really do look different from each other. And that also helps quite a lot with a system of this sort. Obviously, the post office has invested a tremendous amount of resources and effort into this, and their commercial grade systems are really rather good. From this assignment, though, there were some important things that I wanted you to learn that I hope came across. First, of course, is the whole notion. So I'll even change color here to blue. Yeah. So some interesting things to learn, of course. I wanted you to learn about the role and concept the hidden node and how varying that number of nodes can have an impact on things. And that didn't work out exactly with everyone, but it did work with some of you. Second thing I wanted to appreciate from this is what is known as no free lunch. That is, every data set differs. You know, I had you each create your own data and run the numbers on it. And a lot of what you all got to see today is that you were getting wildly different results. You know, and a lot of the reason for this is that different approaches went into the creations of these data sets. It can be really hard to appreciate this if you just sort of are given off the shelf 60,000 things and build your classifier. I mean, there's obviously a role for that, but I wanted to give you a feel for how every data set is different. And because every data set is different, you can't automatically predict that some particular outcome is likely to emerge. You know, you ultimately have to get a feel for what does this data set even need? You know, so if you're out in the field trying to build a classifier, of course, I'm speaking of field metaphorically, you're probably in an office somewhere. But if you're out building a classifier in some real world situation, you can find as the data comes in that you do a lot of tweaking of the algorithm to decide what kind of classification scheme you need. And ultimately, you're going to want to try multiple things, you know, not just one particular algorithm, ultimately. So, you know, there's really no free lunch in terms of finally being able to say, you know, if I've got 27 hidden nodes and a learning rate of 0.14, I will always have the perfect classifier. Because you won't. You know, it's really going to depend a lot on the characteristics of the data. And in this case, a lot of it came around to saying, it may be a Y, but there's so many Ys. There are so many different Ys. So, you know, the notion of the hidden node, the idea of no free lunch, the general black box aspect of the multi-layer perceptron. These things are just not easy to decode. Like, what is it precisely that a given hidden node has learned? You can do some experimentation to try to identify this sort of thing. So for instance, you might feed in some examples from different classes and see if particular hidden nodes are more or less likely to be active when particular examples come in. And so that can give you some ideas about what the hidden node has actually learned. You know, which is pretty interesting, but still somewhat opaque. In other words, you throw a lot of stuff at it, you get a way to examine, okay, this hidden node really likes H's and R's, but good grief, it hates K's. But it still becomes pretty difficult to figure out what exactly it has worked out when thinking about that general space, you know. So all of that said, where these tend to really work well is think about modeling some kind of continuous space of examples. You know, if you've got enough examples where you can imagine one thing kind of fades into another and so forth, the multi-layer perceptron can often work pretty well. But its opacity, its black box aspect can be absolutely maddening. Yeah, Dan, you have a question?
When you're saying one thing morphs into another, are you meaning you have enough examples where all your C's eventually morph into each other? Or are you talking about where one distinct label can actually morph into another and kind of got a continuous change from?
It was kind of getting more to the former. So if you imagine, say, having a couple of letter C's. So here's a C, and then here's a C. And, you know, maybe it's just shifted a little bit. And typically you need a lot of these to get to this point, right? And so ultimately you go through enough of these and then you might eventually get to a C over here or something like that. But if you've got a lot of continuous examples that have a lot of overlap, it gives the multi-layer perceptron a lot more to work with, to operate with than otherwise. So cool. Any questions, further discussion about the multi-layer perceptron? Yeah, Jake.
How much do you think the difficulty would increase if we were to do like cursive letters?
Well, that's an interesting issue. part of the trick with something like cursive letters is the degree to which they mutate based on their neighbors and based on their predecessors. And actually, this too is something that's often used in commercial grade systems, is to try to eliminate ambiguities by building a predictive model of what letter tends to come after a given letter. So what that can do is greatly reduce the search space. So you can imagine saying, for frequently chained combinations, you can actually build specified classifiers that are only trying to distinguish among things that are likely to come next. So if I were to do cursive, I would absolutely have to engineer it in the context of a system like that, based on some kind of predictive model of what comes next.
I just figured since I was getting confused with like R's and K's, there's so many loops and curves and stuff. Cursive letters that could be
Right. I mean, the thing with cursive, right, is when it's done neatly and beautifully, it's very, very easy to read. And when it's done hurriedly, of course, it's less easy to read. So yeah, cursive could certainly be tricky. Anything can be tricky with a multi-layer perceptron. Yeah, Dan.
Is it correct to say with this stuff that your R is just sort of limiting how much it can change for each training iteration?
The rate, yeah.
The rate?
Yeah.
And so that small R's shouldn't require as many iterations as larger R's?
Well, they can require more if drastic changes are needed. Yeah, so it really kind of depends on how the network starts out. Like with a low R, it's going to take a while for it to do anything interesting. But then once it's gotten somewhere good, it's really just doing fine adjustments. With a bigger learning rate, it tends to jump around a little bit more. But what you want then feeds right back into characteristics of the data set. There winds up being no real substitute for experimentation and kind of massaging the data set to figure out what it needs to be like. Data is like really prickly. Yeah, in a sense.
That's another question that's probably not like connected to this, but you know how we use the Connect Vision and Kennan to classify sentiment analysis of tweets? Can you do an attempt to classify tweets or sentiments using neural network, and how bad or good can that be?
So the answer is sure you can. The key is you have to figure out how to encode them as binary values. So the inputs to a neural network have to be binary. So that said, I mean, you can do that, right? So for instance, you could use so Unicode encodings are 32 bits. So you could certainly imagine some kind of a classifier that can handle a sentence of up to, say, 100 words by 3,200 inputs. That sort of thing. I mean, that might sound like a lot, because it is. And if you're restricted, say, to Latin letters, you can just get away with 8 bits. Actually, with Latin letters, you can get away with 7 bits per letter. And then you can reduce the input size quite a lot. You really only need the 32 bits when you're going to like Chinese and that sort of thing. But yeah, you could certainly do it. You could certainly do it. I mean, you could narrow it further. You could say we only care about Latin alphabetic letters in one case. And at that point, you go down to 5 bits, since 32 is bigger than 26. Yeah. And that even allows for a space and a little bit of punctuation. So yeah, so you can do stuff like that, but you can also try to come up with other schemes. They might be, you might have a dictionary, and then you might numerically say, word 100 winds up getting classified like this, and you encode the 100 in. So there are different granularities of representation, but you can certainly apply this. Yeah. Yeah. So, other discussion so far. Yeah.
When we did all of our weights were initialized randomly. Are there any cases where you initialize a weight to some given known value?
I mean, you always can. The trick is, what's the basis for coming up with it? In other words, maybe you're trying to seed the network with some particular initial outcomes. So you can do that. If you can do that well, you probably don't need to learn. And so I've never found myself doing so. Yeah. That would sort of be the thought process behind it. Yes.
You had down for extra credit that we could look at trying to do one of the K&N or
Yeah.
days kind of things on this. And I give that a brief amount of thought before I
Yeah.
decided that sounded horrible.
Yeah.
And the reason why was because both of those are using some sort of distance metric. And I wasn't even sure how we would incorporate a distance into this kind of algorithm. Maybe just talk briefly about, I
So,
didn't even see where you get started.
right. So for K&N, you could just use Euclidean distance on the pixels. So in other words, you could say, compare pixel to pixel. Actually, because they're just bits, you could actually just use a Hamming distance. In other words, count out of all the pixels, how many of them are the same, or how many of them differ. And the number that differ is the distance between them.
And then, so that would be in the encoding process, we would encode something that basically had a count of the number. I mean, would
Yeah.
Because
Yeah,
that
so-
wouldn't be binary. Would we want to like encode a file that had a 0 or 1 depending on whether or not that bit was the same?
Oh,
or I mean,
I'm talking just
what we were-
raw K&N, right?
Oh,
So
okay.
raw K&N, which is what I was suggesting there, just use it as a
Okay.
benchmark, not so much to combine it with the multi-layer perceptron. But if you use raw K&N, you just store all the input samples with their labels, and then as a new input comes in, you find the Hamming distance between that and all of the stored ones, and you do the same voting approach, and then you pick the top K. That was more what I was suggesting. Yeah. Yeah, David.
Seems like multi-layer perceptrons take a lot of data in.
Mhm.
If you were to create like a 3D multi-layer perceptron, that just seems like that would just not be able to compute like at all, because you'd have so many connections and so many things. People, like, how would that get used?
A 3D one, I'm trying to visualize.
Like if you had like this is our perceptron,
Mhm.
and then you had another one stacked next to it, another one stacked next to it,
Mhm.
and then they're all getting separate inputs and connected to each other. So if you had like two C's going into two separate ones, but they were comparing their
Whoa.
hidden nodes.
I mean, in a sense, you can do anything, and then it just kind of comes down to how well it does it.
I'm just saying, how well does it scale when you
Yeah.
just crazily add as many things you possibly can?
So let me briefly discuss kind of what the state of the art is for these things, which isn't really what we did here, but part of what we're going to look at next week will help us get a little closer to it. So the state of the art of these is what is called a convolutional neural network. And there are lots and lots of ways to do this kind of thing. But the general concept is to merge into this supervised learning algorithm a certain amount of unsupervised learning, which is what our topic is going to be next week, is unsupervised learning. So I'll just briefly discuss what that involves. Unsupervised learning is about trying to identify what are the categories of things in data without being given any labels. So what are things that just look alike? Any guesses as how we typically decide whether things look alike? Yes. Impose them on each other and subtract it out. So that's correct, of course. Does that sound like a concept we've already explored a little bit? What does that sound like? Sounds a lot like what happens with K-nearest neighbor. Yeah. So unsupervised learning is based on having a distance metric, here it comes again, that is then used to try to automatically figure out what are the different kinds of things in the data set. So how does this play into the convolutional neural network? If you can use unsupervised learning to classify tiny image pieces first, then those image pieces become different kinds of inputs into the network. So imagine, for instance, that an image comes in and you break it up into, say, 5 by 5 subimages. So really tiny subimages. And then you've got some kind of unsupervised learning algorithm that breaks those into categories. And you have to tell it ahead of time the number of categories for it to work with a neural network. There are unsupervised learning algorithms that are flexible about numbers of categories. And the approach we're going to look at next week is actually kind of intermediate between them, which is part of its appeal. But imagine thinking in terms of saying there are 8 kinds of 5 by 5 subimage. I use an unsupervised learning algorithm that lets us classify it into these 8 kinds. And because I'm doing this unsupervised learning, I've got some kind of representative example of each of these. So what the convolutional people do is they take this image coming in and they find, say the 8 representative examples. And then the really computationally intensive part is they use each of these examples as a filter on the image, and they then generate 8 output images, where each image's pixel is getting at how well did the 5 by 5 region around that pixel respond to the representative example. So if it's really close to it, you get a really intense pixel. And if it's not close to it, you get a really dim pixel there. And so typically involved with this also is some kind of a shrinking process or subsampling. And so they do all of that, generate these 8 output images, and then they do it again. And because of the subsampling, what they're in effect finding is one level higher of structure, one neighborhood larger of structure in the image. And then they do it again. And they keep doing this until they've decided enough is enough, and then they feed it into a multi-layer perceptron like we've been doing. And so some of the more obnoxious versions of these have as many as 19 layers, where they just filter and filter and filter and filter until they finally get to the perceptron at the end. Yes?
Okay, so just trying to put this in a more concrete application.
Yeah.
Would it be accurate to say that, like on facial recognition software, this would be like picking out eyes and nose and mouths and then assimilating them together?
Oh, yeah. Yeah, very much so. Faces are kind of a special case in that faces have been heavily, heavily studied. And there are a lot of highly face-specific algorithms that have been developed. But you can do stuff like this on faces and get some decent results. Absolutely. Yeah, faces could be a course. Yeah, as it happens. But yeah, you could certainly. So once for a senior project, a student used the algorithm we're going to look at next week to do faces and got some very nice results for learning. And he had to do some fun stuff like figure out how to get rid of beards and things like that. He wound up focusing more on the eyes and nose more than other aspects. So anyway, so next week we're going to start looking at the self-organizing map, which is an unsupervised type of neural network that's going to have a very different feel than the multi-layer perceptron, in part because its biological inspiration is really different from the multi-layer perceptron. It's thinking about the brain in a different kind of way. And that'll give us just a different perspective and a fun way of thinking about it. I'll disclose my own biases ahead of time. I've done a huge amount of work with self-organizing maps. I love the blasted things, and that'll probably show. So for what it's worth. So anyway, you get the weekend off. I'll see you next week. I'm planning to have the next assignment posted tomorrow afternoon, actually, by request of one student, just wanting to get a head start. So I'm going to strive to achieve that as well. See you next time.